So, welcome to today's seminar. I have the pleasure of introducing Henrik Schumacher from, well, now Leipzig or Chemnitz, one of the two, it's not so obvious.
Yeah.
I think Henrik did his PhD in 2014 in Göttingen with Max Verdetsky. And your topic then was variational convergence and minimal surfaces. So I guess this sort of hints at the work you've done now in later years, except that maybe numerics is a bit missing, which I guess is a very important part of your work.
Yeah, no, it is.
And so Henrik also did postdocs in Hamburg, Aachen, and stays in the US, and I think I remember Athens, and what was the other, Pittsburgh. And now returned to Chemnitz. However, he's temporarily working in Leipzig as a replacement professor for a semester or a year. And now today he will talk about repulsive curves and surfaces. Please, Henrik.
Yeah, thank you so much for a kind introduction. Thank you, Martin, for having me, for inviting me. Yeah, this is joint work with my boss in Chemnitz, with Philip Reiter, and with colleagues from the US, majorly with Keenan Crane, but also with Caleb Brakensieg. He was at the time actually a high school student. He wasn't at the university at all. And Chris Yu, who now works for Pixar. So those people are from computer graphics, computer sciences. So it's a lot of the things what we do is like taking a problem from computer graphics or geometry processing and throwing from some mathematics on that to solve the problem. And actually our goal is, of course, to generate very attractive curves and surfaces, but we use repulsive methods for that. And one of the driving problems is, see, we have some mess of curves in space, and we actually don't know what it is topologically from looking at that. It's just too complicated. And actually, we want to use it for something else. So we actually want to disentangle that. And one idea one could have is, well, let the thing untangle itself, just put some charge on every point of the geometry that repels itself. And then it tries to spread out, and if you're lucky, it gets the clue how to fully untangle. And so the first energy that people come up with is, of course, always like really real electric charge, Coulomb energy. That would be with alpha equal to 1. So you have your geometry M that's embedded by some map into R3, say. And then you say you have a repulsive energy. That's basically you take pairized distances of these points to some negative power, and to take a double integral. Why a double integral? Yeah, you could use a supremum, that would be fine, but suprema are not differentiable, like infinity norms are not. So this is sort of like an LP relaxation of what you actually want to do. And yeah, well, you hope that this energy blows up when you develop a self-intersection, and when you then have a continuous descending flow, you can guarantee that you stay in the same isotopy class. So if you have, for example, a knot, which is a circle embedded into R3, you really want to preserve the knot class during this flow. Okay, that's the idea behind it, but this is how, hopefully this works, how it should work in practice. So I play that again because that's so beautiful. Yeah, so you have this curves that disentangles itself. How useful this would be, and then Apple invented the AirPod and actually made our work obsolete. But that's the idea, and that's something we would like to encourage. Why is this here? I have to click there. Now I'm back in the window. Okay, that's actually the idea, what we want to do. But the problem is that these simple Coulomb-like energies don't work because so you have to choose an alpha here. And whenever the alpha is so large that it could be repulsive, it really is able to, it blows up when two curves or two surface parts come to touch each other, then it actually is not at all well defined on smooth surfaces or curves, because you have a singularity that you cannot integrate when psi equals eta. So you have to do something about that. One way is to put something in the numerator that damps down the singularity, but only where it's supposed to. Basically, when 2 points on the surface are really neighbors along the surface, not in a chord distance in the surrounding space. And one way to do that is this term. You take f of psi minus f of eta, that's a secant. And if you take the normal projection of this secant, normal to the surface, at one of the 2 points, then this gets 0 whenever the other point approaches this point. And if you are on a C2 surface, you have actually vanishing, quadratic vanishing order for eta goes to psi. And then this is actually, this quotient is actually finite. So you have a bounded term that you want to integrate. But when you have two curves, now I want to sketch something. But if you have a piece of curve here and a piece of curve there, and it's not on the screen.
Maybe you could move a bit the camera. So
Have to see the window actually. Yeah, so in order to adjust it, I have to, well, I try to explain it just with my hands. So whenever you have two surfaces that get close to each other, they will do so, if they are closed surfaces, they will do so, the shortest chord between the two surfaces then orthogonal to each part. And then this projector is along this normal projector surface is along the shortest chord. So you really capture the shortest chord. You cannot project it out here, in this numerator. So really you still have the singularity if two parts come to each other, which are not meant to. There is a geometric interpretation of that, of this term, namely, probably you all have seen this construction when we introduce the osculating circle. What we typically do, we take some point and a tangent and we make a circle with C2 contact. And another way to see it is you take, so the orange one is the actual curve. Now you take the point and the tangent, and you take another point, and then you draw the single circle within the plane defined by these 2 points and this tangent line, the single circle that you find there. And the radius of this circle is actually the reciprocal of the integrand. So we integrate 1 over this radius to some power. And whenever this point f of eta moves along this curve to f of psi, then we really approach the osculating circle. That's also a reason why this thing here really converges to the curvature. And for C2 curve, curvature is finite. So the idea is that this tangent point radius is some global notion of curvature radius. And what we then actually do is we compute the LP norm of this. And hopefully this is sufficiently singular to avoid repulsion. And if you take even the L infinity norm, then you have a close relationship to the reach of an embedded manifold. Namely, the reach is the amount you can thicken the submanifold until it touches itself. It's really the supremum of these tangent point radii. So you could view this functional, which is differentiable because it's an LP-based function, as a relaxation of this, of the reach, which is a really geometric notion of curvature. Well, and okay, one can make up this energy, but it's not really obvious that it does what it's supposed to. So it asks for the proof, but there is a proof for rather general sets. Like what you need is n-dimensional sets in Rn with something like a tangent plane that behaves in some way like a tangent plane, and then you can write down this energy, and the result is whenever you have such a thing, and there is a whole catalog of assumptions that you have to add, but basically everything holds for C1, closed C1 submanifolds in Rn. Whenever the energy is finite, then the manifold has to be embedded, and it has to have actually some additional regularity, C1 alpha, and you can really specify this alpha.
Is this optimal, the regularity, or?
Yeah, good question. No, this is not optimal. Optimal is this theorem. It says whenever the energy is finite, it's finite as C1, embedded C1 manifold has finite energy if and only if it is in a certain fractional Sobolev-Soboletzky class. And what you have then, you have the Sobolev embedding from this Sobolev-Soboletzky space into C1 alpha. That's the Mori embedding. And it's a fractional space. So the differentiability of the Sobolev space is 2 minus n minus p. So n is the dimension, and p has to be greater than the dimension. And so you see that the s is slightly greater than 1, and it's always smaller than 2. Yeah, that's sort of built into this energy. It's really fascinating because it's not obvious from the definition of the energy. And even more so, so the next question is probably, okay, you know that the energy does what you want, but does it have minimizers? And also there's an affirmative answer when you you have sort of to bound the overall size of your geometry, because with curvature energies, typically when you just scale the manifold, then the curvature gets smaller. And so the energy goes down, typically. Depends also on the dimensions and stuff. But so you have to bound the diameter or something, and then one can really show that sublevel sets have nice compactness properties, and yeah, one has lower semi-continuity with respect to Hausdorff convergence, which is really surprising because Hausdorff convergence is of course really, really weak compared to this, to the energy space. Yeah?
What if you add the length, not the diameter constraint, but the length into the energy?
Yeah, that's a good question. So actually, that's what we always do. Whenever we minimize something, we fix the length when we minimize it for curves. And for surfaces, we fix the area. And I'm not 100% sure of if we are allowed to do that, but it always works. So there has to be a theorem there. We just don't have it available. But this is a really good question. Well, if you fix the length, bound the length, and for curves, you bound also the diameter. So that's easy. But with area and diameter, that's not so easy. That's a different thing. Okay, so that's the math so far. Yeah, so it makes sense to consider these energies and to minimize them. So what my job is about this is really to do the numerical minimization and to actually produce something with that. And as often when one wants to bring that to a computer, one first has to discretize somehow. One has to resolve the infinite dimensional geometry of curves and surfaces. And I do it here by polyhedral objects. Like for curves, I will use polygonal lines, and for surfaces, I will use triangulated surfaces or triangle meshes. One could also use piecewise polynomials or NURBS surfaces, but we just didn't do that because piecewise linear things are sort of easier to handle, especially when so many nonlinear things are going on. Well, and then the easy idea is, well, once we have to discretize and we have a finite dimensional problem, so we can just throw our black box minimization tool onto that. But it actually doesn't work that well. So there are many reasons. So I said why we want to use polyhedral surfaces, but the problem is polyhedral surfaces don't have finite energy. Remember, we have C1 alpha continuity for finite energy, and polyhedral things have corners or edges, really hinges. So they actually don't have C1 continuity, so they cannot have finite energy. So what we have to do, we have to invent some discrete energy that in some sense resembles the smooth one. And well, in the end, there has to be a theorem that one proves something like gamma convergence of this discrete model to the smooth one. Yeah, we are not that far yet, but the experiments are super convincing that we did it correctly. And the next thing is that when you take your favorite black box optimizer, it certainly won't work pretty well. One issue is, well, the best way would be to use Newton's method, but then you have to compute second derivatives, which is super expensive. I will explain why. You have to solve a super expensive linear system, first build and then solve it. And everything other than Newton's method really performs super poorly because of ill conditioning. And our way out is to build a certain type of preconditioner, yeah, we used to think of it as a Riemannian metric, just to work in the right metric space. Yeah, think of the CG method if you use Euclidean inner product to minimize in the minimization of some really degenerate quadratic form, then it's super slow. But if you have the right preconditioner, it just makes the optimization process much better. And actually in this preconditioner, that's where the knowledge about the energy spaces enters. And the third issue is, remember, our energy was defined by double integrals. And if you discretize that in an easy way, you represent your curve by a polygonal line, and then you sort of have to sum for every pair of edges or every pair of vertices. So if you have something like n particles, you need n squared interaction terms to sum up. Yeah? So these double sums are super, super expensive. Curves, it's okay-ish to do that if the curves are not to resolve too finely. But for surfaces, one has to invent something else, and that's what we did. And what we do is we adapt techniques that are already known to work for n-particle problems, where one actually also uses like the Newton potential, which is actually the Coulomb potential. And we use those techniques. We have to adapt these techniques, but I'd like to explain how these work. But first things first, we have to find some discrete notion of energy. And what we do is basically, we say we represent our smooth manifold sigma, the surface, we represent it by some simplicial mesh, like a triangle mesh inscribed or a polygonal line inscribed into that. Closely inscribed, that's the subtlety, like the normals of the surface have to be approximated by the normals of the triangles, which is not, one has to do some additional work in order to enforce that. And then we need these normal projectors. If you have an edge of your polygonal line or a triangle in your triangular mesh, the projector is just constant on this face, on this line or triangle. That's not an issue. And still one has this integral over 1 over the positions. And what you do simply there, instead of computing the whole integral, we just take the barycenters, we evaluate, we do the midpoint rule on the product of triangles or of edges. That's the formula, but well, here's also an illustration. So the blue thing here is the smooth curve, and we inscribe some polygonal line, and when we have two edges here marked in green, we take their barycenters and the connecting vector, that's what goes as norm into the denominator, and we take the projection of this vector onto this normal plane, which I indicate here by the circle or by this disk. So this is the projection, and its norm enters in the numerator, and that's it. And for surfaces, the thing looks like this. We have here a blue saddle surface. We sprinkle some point and then we gray, then we replace it by a triangle surface. And whenever we have two faces of this triangle surface, again, we take the barycenters of these triangles project them to the normal direction, and then the connecting vector is in the denominator, and the projected chord is in the numerator. And that's the energy, just a double sum over all pairs of triangles. And I said, well, actually, in the end, one needs a theorem that tells us when we discretize in this way, solve the discrete problem, we really approach the smooth solutions. That's not done yet, but a typical sanity check that one should do is take a smooth surface of which you know the true energy, discretize it in a neat way, and hope and see how your error evolves, the so-called consistency error. So that's what I do here. I took a slightly wobbly torus. Yeah, it's not the perfect round torus. I added actually some sine waves to it because, well, there is a lot going on a perfectly symmetric surface. Many errors can cancel out, and also the obvious mesh that you could do there is too regular. So we took a smooth surface, which is quite wobbly, and then we discretized it, and we recorded the true energy, which is E. Actually, we didn't compute the true energy, but we used some adaptive, really expensive adaptive integration rule that guarantees that we approximate the true energy by 6 digits, which is more than we need here. So this is basically the true energy EH. H is the typical edge length in this discretization. E minus EH is the error, and dividing by E means it's the relative error. And I also recorded the time we spent on computing that. And if we decrease H roughly by the factor 1/2, then we get 4 times as many triangles, because basically we subdivided every triangle into 4. We see actually the error decreases, and of course the time we need to compute that increases. So after a couple of steps, one cannot even see the triangles anymore. It's so many triangles, but you see here the number of leading zeros that increases. So this shows, this is a good hint that this energy discretization is a good one, that it is at least consistent on smooth objects. If we sample them in a nice way, then we can reproduce the actual energy up to some small error. But you see also that computation time grows quite quickly. This is just for computing a 300,000 triangles is actually not that much for the computer model. And we spent 5 minutes just for computing the energy. Of course, one can parallelize and blah, blah, blah. This is just, I think, one core machine that did this. But the time just computing the energy scales quadratically. This is not an option. It actually is forbiddable for any prohibitively expensive for any reasonable application. So we have to do something about it. That's the thing with the double sums. You have to get away from the double sums. Then I don't know, how late is it? Just to get a hint. Ah, there's the one. Oh, there's the clock. Okay, great. Good to know. Okay, so next thing I'd like to cover here is the problem with the optimization, that actually black box solvers don't work that well. And just to show you, whenever you take black box solver and you give him this energy, that what they do basically, these typical gradient methods, is in one way or the other L2 gradient descent or L2 gradient flow. And when you put that into this solvers, they automatically do a line search in terms of the PDE that you solve. You try to guarantee that the discretization stays stable. Because it's explicit Euler, you need small time steps in order to keep it stable. And the optimization, the line search and the optimization method tries to adjust the step size in order to keep it stable. So you make tiny steps. And I have here a very simple trefoil knot, and I added some really nasty noise to it. And when I run this L2 gradient descent, that's what happens after the first 10 gradient steps. So it hasn't changed at all. And think about it. Every time we do a step, we have to spend at least 5 minutes in order to compute the energy. So after 50 minutes, that's what comes out. Actually, way longer than that. If you think of this really fine surface, of course, this is a really coarse curve. It was much quicker. And after 20 steps, what you see and what's quite typical for L2 gradient flows is that you have some nice local smoothing, but the overall shape of the curve doesn't change too much. And the reason for that is basically, if you consider the L2 gradient, that's basically the vector field that is, so the L2 gradient is of the energy is a field along the curve, vector field. And it's the force, actually. Physically, it's the force. And you know, if you have a repulsive energy and you have things that are really close to each other, then the forces are super large. So that's what happens here. You have these immense force spikes. And then you have regions of the surface where you cannot see the force. There is some force, of course, but it's super small. And here you have these spikes, and that tells you have to be really cautious, really take tiny steps in order to progress. That's basically the reason. And the second reason is when I add a bit of noise to the curve, then this is what the gradient does. It's super discontinuous, sort of, with respect to certain, it's a really nasty perturbation, I have to say. But it's actually the fact that the energy is not differentiable with respect to L2 norm. That's all it is. It's just not appreciably differentiable. So the L2 gradient is not at all a good differential in that sense, or not, at least not a good gradient, not a good search direction. So one way to overcome that is to return to this result that stated whenever the energy is finite, you have a certain smoothness of your functions. And the idea is, well, when you do some gradient descent and you compute your gradient, you have your current state, and you add the gradient to that, or a small multiple of that, you want to stay in the same Sobolev space. You don't want to lose regularity. Otherwise, you cannot do the next step. That's the issue. And so we want to do something that repairs the fact that the differential is a thing that lives actually in the dual space of the Sobolev space. And you need a way to get back from the dual space to the primal space in order to say, I really make a finite step in that direction in a stable way. And now it gets a bit hand-wavy. The problem is that our energy space is not a Hilbert space. If it were a Hilbert space, we would just take the inner product of that Hilbert space. But what we can do, and which actually works in practice, is we take the Hilbert space that in some sense is closest to that. What we found the most important information is the differentiability, how many differentials you need. And we just relax from L2 to from LP to L2. P is typically larger than 2, so this is a weaker space actually. And we can take some HS in our product there, which you can always, for example, one way is to take some fractional powers of the Laplacian. Laplacian has order 2. If you take it to the power s over 2, then you have a differential operator of order s, and then you take the L2 norm of these operators applied to your functions u and v, and then you have the HS norm. So that's the idea, not to use the L2 inner product to compute gradients, but this HS inner product. But the problem is, okay, we basically can do that. We have our discrete geometry. We know what a good Laplacian is there. That's finite element Laplacian, cotangent Laplacian on surfaces. We can build it, and we can apply eigenvalue decomposition to take a fractional power of that. But it's super expensive, because that, if you have n points, computing eigenvalue decomposition costs typically n to the power of 3. Actually, this matrix is a dense object. It's a dense matrix. You actually don't want to build it. So we try to do something else. And when you consider the the formula for the fractional Laplacian on Rn. And this is now the fractional Laplacian of order S, which is larger than 1. Then you actually get a formula like that. Say M is Rn, Euclidean space. These are the conventional dx and dy derivatives. And this curly d is just the differential of u. And you take differences and you have to divide by certain powers of distances. And that's your fractional Laplacian in Rn. What you can do is you take just this formula and place it onto an embedded manifold. You replace the distances in Rn just by the chord distances, and it actually works. It has the correct principal symbol. It really has the principal symbol psi to the power of s. In some way, one has to apply some pseudo differential operator theory in order to see that. But this is basically, it's easier to work with because, well, if you discretize it, this just becomes an n by n matrix. Yeah, you have double integrals again, but we know basically how to handle integrals. We don't have to do eigenvalue decomposition anymore. So that's why we can use that. So if you want to compute the gradient, let's say u should be the gradient afterwards. What you have to solve is the equation, scalar product of u with an arbitrary test function v is the same as the differential of the energy applied to v. So basically what you have then, you take your discretization, the differential is a vector, the Gram matrix of this inner product is a matrix, and you have to solve the matrix equation to compute the gradient. And then actually what turns out is that you get gradient vector fields, which even if you don't have a Hilbert space, it still is Lipschitz continuous when you already start in a slightly smaller Banach space. And the advantage is that your PDE, that you basically gradient descent and L2 gradient flow, they are really close to each other. So they suffer from the same problem. So if you view this L2 gradient flow as that's a PDE, where you really feel the time discretization is not independent of the space discretization. But here with this Sobolev gradient, what you get is then an ODE in the time direction. You have to solve spatial differential equations in every step, but it's an ODE. You really have a Lipschitz continuous right-hand side of your differential equation. And this makes it much easier to solve this flow or to compute the gradient descent. And here's the direct comparison. On the left, same geometry as before. On the left will be the L2 gradient flow. On the right, it's this HS gradient flow. It's actually not for the tangent point energy, but for an energy that's quite similar to that. And now I go step by step, and you see, so on the left, almost nothing changes. On the right, so. But I go further and further. And after 10 steps, you basically reach the minimizer. That's how we expect the minimizer to look like. And after 20 steps, nothing has changed, which is really convincing that the minimizer of this energy should be that on the right-hand side. So we could have run that for 100, 200 further iterations, and it wouldn't have converged. So this is why this practically this HS gradient flow or gradient descent speeds up the optimization part immensely. So whenever you factor that in, that you use these HS gradients, every black box solver basically can work with that. Instead of feeding the L2 gradient, feed it the HS gradient. So that's the adjustment we have to make for the solver. And let's get back once more to this spiky behavior of the L2 gradient. Now in comparison, that's how the simple SH gradient looks like. So it smoothes out these kinks. So this is more predictable. So one gets a glimpse that it's easier to do update step with that, can take larger steps. Actually, we make some subtle additions to this inner product that penalize regions where you have almost self-intersection. And then this gradient field is actually scaled down where the gradient is particularly large. And then where the ends are free to move, they really move there. And that really helps. We have to see that actually in practice. That will be the slide after the next slide. Another thing is that this whole process is super robust under noise. So the gradient is slightly different, but you can imagine that it won't get completely nuts after you have this perturbation. And of course, in every numerics pipeline, you have here or there some sources of noise that you don't have really under control because you didn't care to implement something really cleanly or something. Yeah, so it's really more robust than L2 gradient flow. This is the modification of the metric. I actually don't want to mention too much about that because time is running and I want to show you these movies. This is example of a curve that was designed by Friedman, He, and Wang in the work on the Möbius energy, another energy that's supposed to untangle knots. And they say, well, this is actually an unknot, so it's homotopy equivalent to the round circle, but we don't believe that there's any energy that can unfold it because they really did their best to entangle this. And let's just see what happens with the flow. And obviously it's doing well. So I can slow it down a bit and run it once again. That's what goes on. And what you see is that it's really important that the strands of the curve that are away from the rest, from the mess in the middle, they can move. For example, really, this is so annoying. No. Yeah. I have to live with that. So this configuration is almost what you saw in the pictures before with the gradient. And what you see here, actually this loop, why is my pointer frozen? So this loop over here has to go through this other loop. We see that after playing around with that. So actually there's no point in moving the middle too much. So it's really often what's at the very outside of the knot that's to be moved. And this is what this inner product really does quite well. We don't have a real proof for that, but just it's quite convincing. It does what it's supposed to. It produces the round circle in a couple of hundred iterations. Okay, let's go on. Here's another example. Whenever I have something blue, blue means it's a surface. Orange typically means it's a curve. So this looks curve-like, but it's actually a surface. And that's the second paper we wrote together. It's about applying all these methods to surfaces. And here's a quite similar thing. The L2 gradient is quite Dirac-like in regions of near self-contact. And this is how this Sobolev gradient looks like. And it's really like the whole surface moves. You don't waste any iteration on not altering something at some points. Yeah. This is quite neat. And this is why it's basically works so well. It's still not perfect, but it works surprisingly well. And then the last issue I'd like to explain how we solve it is the thing with the double sums. And remember, we had to sum over all pairs of triangles on the surface. Now I'm just talking about surfaces, all pairs of triangles. But when you consider the error bounds for the midpoint rule of these two triangles, what you see is actually, you can also say, I take two arbitrary patches on the surface, S and T, and let's say they are quite distant from each other. You take some convex bounding volume like axis aligned cubes, and you say these diameters of the cubes have to be small compared to the shortest distance between the two cubes. So this is this inequality. So both patches are small. Theta is considered to be a small number. The diameter of the patches is small compared to the distance of the two patches. And when you analyze the quadrature error of the midpoint rule, what comes out is, well, this is the midpoint approximation that we do. Just take the midpoints, let them interact, weigh them. What you get is something like the error actually depends only on theta, not on the absolute size of the patches, but on theta. Well, it's theta weighted with the areas. But if you can guarantee that you can decompose your manifold times manifolds into such patches, then you can simply say, oh, instead of, let's say, there are 1,000 triangles in this green patch and 1,000 triangles in this red patch, instead of computing 1,000 times 1,000 interactions, you just compute one interaction with a controllable error. And this is basically the point of Barnes-Hart approximation or fast multipolar approximation. Multipolar approximation actually would not only use the midpoint rule, but would expand the Taylor polynomial a bit further, not just the zeroth order term, but we just do first zeroth order multipole, which is also called monopole method. So that's the point. So instead of, if the patches have size n, ns, and nt, instead of ns times nt flops, we just need one flop, let's say, yeah, to compute that. So this is where you save all the work. So the rest is about, we really have to integrate over m times m, the cow times the cow. What we have to do is we have to decompose the whole surface into this product into many of these patches that all satisfy these theta condition. And there is actually a neat way to do that. And actually, this is about tools that are actually frequently used in computer graphics. So when I read numerical literature, for example, by Hackbush on cluster trees and block cluster and hierarchical matrices, they call this tree that I built now, they call it a cluster tree. In computer graphics, people call it a bounding volume tree, or one could call it a binary search tree. But the idea is divide and conquer. So this is the whole surface. What you do then, you do some greedy split along an axis in order to produce patches that have smaller diameters, and you do that further and further, then we get this binary structure. You store the structure, even further. So in the lowest levels, the leaves of this tree will only be only few triangles, or even a single triangle. That's also possible. So it's actually much deeper than you see here. And then you try to cover all of m times m by pairs of such patches, and you proceed as follows. You start with the root. You build a new tree, actually, and you say the root of a new tree is m times m, the whole geometry times itself. One calls this also a block. A node in this tree is called a block, because if you make such a matrix diagram, it's a square, it's a block. So, and you cannot go with that because this theta condition is, of course, violated. So what you can do is you split in both axes. Then you have these pair of patches, and then this node, this block, has 4 children, which are smaller in size. And these are still not admissible. They don't satisfy this theta condition. So you split them again and again, but at some point you find pairs of patches. This pair and this pair, they satisfy the theta condition. So I mark this block green and stop. This is, I can replace this. The area of this block is proportional to the work I would do naively, and I replace it just by work one flop. And I can proceed and proceed. And I think that's the deepest level I showed here. So you get a decomposition of m times m in mostly green blocks. There are some red blocks remaining, mostly, especially along the diagonal, you always have, because that's triangles that basically are really next to each other. And even these blocks would go away if I divide further. I just stopped here in order to be able to plot it. So when you have this decomposition, you just sum over all greens and all red blocks. And the point is that, yeah, you had n by n block pairs of triangles, and roughly, because you use a binary tree, the work that you have to spend in the end is n times log n-ish. It really depends on the distribution of the surface in space, but typically one says n times log n. And as Keenan used to say, log n in computer graphics is a constant. It's basically linear in time then. Yeah. And we can use to compute the energy, its derivative, and actually also to solve this linear equation with the inner product. We can use the same strategy also here. Here I only show you how to use, how we did that for the energy. So this is the old table I showed you in the beginning with these 5 minutes of runtime, just to compute the energy. And here EHFMM means fast multipole method, which is just the fast monopole method. And I show you also, of course, the relative errors and the time that we need. And yeah, for this fine, so this grows linearly, this grows quadratically. So there's at some point, the almost linear method, of course, wins. So this is something, it's now seconds and not minutes. That's tractable. Well, this is a log plot. Some numericists love to see those, but just to wrap it up a bit before I go to the actual experiments, because that's real videos, what we can really do with that. This is once again showing you the thing about the fractional inner product. So we have an example here, one and the same geometry, but meshed in different resolutions. So this is a coarse mesh, medium, and this is fine. And when we just run this L2 gradient descent, basically the same algorithm, but with the L2 gradient, then we see, well, when we run a fixed number of optimization iterations, that's what we end with. It has basically not changed at all. H1 gradient and H2 gradient are sort of better, but they both have their defects. H1 is better to smooth small features. H2 better smoothes out large features, but they have problems with the other frequencies. Yeah? And HS in the middle is really the sweet spot. It's really the, yeah, there's no point in using you really need the right inner product to do it correctly, the right differentiability. Yeah, then basically you need the same number of iterations for all mesh resolutions, and this is really fine. So now we really want to see actual examples, and this is, for example, a nice thing, because when we look at these two surfaces, well, they are actually bronze. It's not blue, it's like orange. So I have to say, these are surfaces. Can you make it a bit darker now?
This is the color.
No. So yeah, then there's no other way to do that. Okay, so when you look at that, everybody who sees this for the first time would say those two are topologically inequivalent. There's no way to deform one configuration in the other. They are really interlinked. And what we can do now is run the optimization on both ends. Well, I just show the video and then I tell you what happens. Yeah. So what you produced is actually what's called an isotopy, yeah? A path through the space of embedded surfaces or ambient isotopy. Yeah? So these are actually deformable into each other. And what we did is basically we took both configuration, flew it to the minimum. It happened to be the same. And then we just reverted one of the videos and glued them together. Basically, that's also what people did for this sphere eversion. They took a symmetric Morvan surface like Kusner and Sullivan, they did it. They took a Morvan surface, which is sort of symmetric, and it's a saddle point, and you could take the Wilmot flow down both directions of the saddle. And in both cases, you happen to end up with a sphere, but one sphere was turned inside out. And this is sort of similar. Just we flow from the two different maximizers to a common minimizer. Yeah, this is a nice, really nice.
So you could even say you do machine learning, but
well, yeah, fair enough. So somebody took our material and made a YouTube video out of it and had actually an advertisement for some machine learning business on that. And everybody in the comments said, oh, this is machine learning. It's not really, it's gradient descent. Some people say, well, machine learning and nothing else than, okay, but this is a different topic. So here's another example. So imagine we have an infinitely long pole, or just say the silver thing is just a huge circle that's closed, but there's no way to take this loop of this double torus up and remove it. So you would say, oh, this is non-trivially linked to this infinitely long pole or to this other ring. You can make it a finite ring, a key ring, and this double torus. And let's see what our algorithm does with it. We just minimize the tangent point energy, nothing else. And voila, we've removed one handle from the pole. Isn't that magic? And now it does it in reverse so that you really see this nice transition.
did you add repulsive forces to the tube, to the metal tube, or?
Yeah, actually, it's actually also the tangent point energy. So we apply the tangent point union to the union of the two, but we just fix the pole. It is not allowed to move. And now this is it in reverse. Yeah. Actually, we do something else than just applying tangent point energy. When you minimize, you get basically something like this. And my collaborator Keenan didn't like it. He said, I really want to show people that it's the double torus. So what he did, he took two invisible repulsive planes and pushed them to the middle. And that's why this spread out. And that was to show us that it's really the unknotted handle body of genus 2 that comes out of this. And of course, we tried many things like this. Yeah, so we took a trefoil knot and then we attached such a loop there. Can still, I don't know, but it's a surface again. Yeah, so it's a thickened, it's a tube around the trefoil knot. Let's see what happens here. Unfortunately, now the camera position is not ideal. But afterwards, the camera turns around the object and you see what comes out. And this is actually, well, you see probably 3 holes. But again, it's the handle body with 2 handles. It's genus 2. Yeah, if we could press it again and we get again the double torus. Yeah, and it was so surprising to end up with that we at some point thought, are there at all knotted surfaces? Here's another example. This is like the handcuffs example, what I showed you in bronze. But this has just gone wild with many loops around itself. And now I think I can speed it up a little, otherwise it takes too long. Okay, we then thought, okay, now it has to stop. But no, it went on. And it actually reached again at the handle body of genus 2, the unknotted handle body of genus 2. We were really surprised that this algorithm was able to do that, because it's really, apart from computing this gradient with respect to another inner product, it's just gradient descent. And then we really asked, are there actually knotted genus 2 surfaces? And Keenan had a brief look into the literature, and then he found out, yes, people studied actually knotted graphs. And if you thicken a graph, you get a surface. And if the graph was knotted, then it's quite likely that the surface is also knotted. So this is some table, like whoever has seen knot tables, this is the same thing just for theta curves. It's graphs of 3 edges with 2 points of valence 3, because they are topologically like a circle with a bar in it, that's a theta. And so they are sort of classified. So what Keenan did, he wrote a quick script to take each of these, make it a tube, and then flow, minimize this tangent point energy with some parameter p, and that's what comes out. Yeah, so this is the first time that anybody saw the energy minimizers of these tangent point energies for knotted surfaces. So really, well, we conjecture, of course, these are minimizers. We cannot be sure. At least these are probably local minimizers, but we cannot be sure. And so this was genus 2. So Keenan also asked himself, what about general genus? And the easiest way to build a surface of high genus is, well, either take a sphere and glue handles to it, or just take many donuts and glue them together. And actually, this is easier as the thing with the sphere. And then he minimized them with many different genuses. And what's really surprising, this is the one that we had before, genus 2. Genus 1 is just a round torus. Apparently, this is not surprising. Genus 0 is, of course, the round sphere. But even for higher genus, sometimes you have really beautiful symmetries, like here tetrahedron symmetry, here the symmetry of a cube. These are like prisms. Then there are some measurement errors. Well, there is probably no interesting polyhedron for that. But what we were really surprised is genus 11 that belongs to a dodecahedron. We are not 100% sure if this is really a minimizer or just a critical point. Often you have that with geometric optimization problems, that if you put too much symmetry into the configuration space, then you get spontaneous symmetry breaking. The minimizers are not that symmetric, but you get many of them because you still have the symmetry on the set of minimizers. So we are not totally sure of this, but it's really interesting that this regular thing comes out, because we haven't started with a geometry that is symmetric. Yeah, it's really, we start with a chain of 11 donuts just in the plane, and this contracts somehow into this roundish thing. Really surprising. Okay, that's it already. There are, of course, many further questions one can ask. So it's, for example, not clear whether our energy is really a good approximation for the smooth thing. Actually, one needs something like a gamma convergence result, but that's, well, from the point of applications, there's no point in first proving that the energy can be discretized before you have established it as applicable to what computer graphics people want. And actually to them, it's good if it does what it does on their examples, and they don't not necessarily need to prove. One can work on many questions like accuracy or performance of the optimization, close to the minimizer. One actually wants to do something like Newton's method, which would behave better. And yeah, well, many further questions, but for now, I thank you all for your attention. And there's another short collections of things that we can float. So sort of like that's sort of the idea is you have now some canonical shape a topological surface of some genus has, so you can use that for classifying things or something. Well, actually, it's easier to determine the homology group of the thing in order to know how many handles there are. Unfortunately, these are all unknotted examples, but in principle, it's that would be also something like a dictionary of surfaces in terms of these canonical surfaces. Okay, but thank you all for your attention, and I'm looking forward to questions.